Okay, continuing on, we are going to be looking at this next formula right here um, in this section, which says the speed of light equals the wavelength times the frequency. So because the speed of light is constant, constant such that, it's the speed limit of the universe, is the fastest that light can go is in space, in a vacuum. Because this number is constant c, that means that if our frequency were to increase, that our wavelength must decrease proportionately. And the reverse is also true. If our wavelength increases, then our frequency must decrease proportionally so. Such that if I multiply these two things, I always get the speed of light. Now, because these wavelengths are so small, to write them out in scientific notation would get to be very cumbersome. So we're going to want to use this unit nanometer. We're going to want to remember that equals times 10 to the negative ninth. We also have micrometers and pentameters. We're going to primarily use nanometers, but whenever we're using the formulas, we will have to convert to meters. So the wavelengths are given. We're going to find the frequency. So we're going to use the second formula, C equals lambda times frequency. And we know the speed of light, and our lambda is going to be, this is a wavelength. How do I know? Because it's in meters. Frequency would be in hertz. So I have 800, but I'm going to tack on, because I have this nanometer, times 10 to the negative ninth. Okay, so now we're ready to go into our calculator here shortly. We're going to divide by this 800 times 10 to the negative ninth on both sides. And that should give us our frequency. So we'll switch to our calculator, and we'll go C divided by, I'll make sure I put this in parentheses, 800 times 10 to the negative ninth. All right, and we will get 3.75 times 10 to the 14th. Was it negative? Nope, positive. Positive 14th hertz. That's pretty fast. All right, so next one. Or, yeah, you know what I mean. Okay, basically it's going to be the same thing over and over again. So C equals, this time 625 times 10 to the negative ninth. Frequency, and divide. Okay, and on that one, 4.8 times 10 to the 14th. And hopefully you get the pattern here. I'm just going to substitute that in. So I don't think there's a need to do the third one. All right, let's take a look at the next set. We're going to go the other way. And so it's really going to be the same thing. The frequencies are given. Let's find the wavelength. So we're going to use that same formula, C equals lambda F. C is the speed of light. This time we're finding lambda. And our frequency is 5.4 times 10 to the 22nd. So it actually works out exactly the same. C divided by, now make sure I'll throw this in parentheses, 5.4 times 10 to the 22nd. And 5.56 times 10 to the negative 15th. Okay, let's try this next one. Same thing. Looking for putting in our frequency. Go to our calculator and solve by dividing. and 4.47, so 4.48 times 10 to the negative 7th. Now, all of these are wavelengths in meters, and I think you get the point, so I won't do that last one. And now this is going to be a tricky question. How many wavelengths of light can fit in a distance of 2 meters? Well, I'm going to need to know, 2 meters. Let's see. I'm going to need to know what the wavelength actually is on this. What is the wavelength? So let's just choose one of them, because I didn't give it in the problem. Let's say I have a wavelength of 500 nanometers. So I'm basically finding how many nanometers can fit into 2 meters. So I'm going to take my 2 meters times, let's convert that into nanometers. So the larger unit, well, I need to go 1 meter, and there's 10 to the 9th nanometers in 1 meter. So that gives me nanometers. So I'm going to get 2 times 10 to the 9th nanometers. Now I need to know how many times this 500 will go into that. So I'll divide this by 500. Two times 10 to the 9th. I'll make that a quantity. And I am going to divide that by 500. And there we go. 4 million. All right, short section. So good luck.